Welcome to electrical machine lecture. Uh, Today we will do few example on the topic Swinburne test or no load test. So the example is like that: a 200 volt shunt motor develops an output power of 17.158 kilowatt when taking 20.2 kilowatt. It means that the output of motor at particular condition, loading condition, is 17.158 kilowatt, whereas corresponding to this output, the input is 20.2 kilowatt. So here it is given that input power output power is equal to, it is 17.158 kilowatt, which is equal to 1700 17,158 watt. Corresponding the input power for this particular output of the motor is 20.2 kilowatt. It is 20,200 watt. So this is the input and this is the output. The field resistance is 50 ohm and armature resistance is 0.06 ohm. What is the efficiency and power input when the output is 7.4 kilowatt? So it is asked in the question such that if suppose this is the condition, input and output power, what is the efficiency at this particular load? We want to know what is the efficiency at this particular load. So from this given data, it is possible to calculate the no load losses. And if we are able to calculate the losses, sum of the losses, then that losses is going to use in the given condition. So we can say that the total losses is equal to power input minus power output. So the difference of these two is nothing but the losses. So it is 20,200 minus 17,158 watt. So it is equal to 3,042 watt. So this is the power loss at this particular condition. Now, once we know the power input, it is possible to current the input current or the current drawn by motor is equal to power input divided by applied voltage, or simply it is the voltage. So the applied voltage is 200 volt. So it is 20,200 divided by 200 volt. So it is 101 ampere. So this is the current under such particular condition. Now, shunt field current ISH is equal to V, that is terminal voltage, divided by RSH. It is equal to 200 divided by the resistance is 50 ampere, 50 ohms. So it is 4 It is 4 ampere. So what is the armature current? Armature current is equal to 101 minus 4 equal to 97 ampere. So this is the armature current taken by motor under above condition. That is, the input power is 20.2 kilowatt and output power is this much. Okay. So therefore armature copper loss armature Cu loss is equal to 97 square multiplied by the resistance of armature circuit, which is given as 0.06. So it is 2478 watt. So this is the power, sorry, it is the it is the 500 500 564.5 watt. So this is the copper loss. So once we know the copper loss, we know the total losses. So the difference of these two is nothing but the constant loss. So therefore, constant loss WC is equal to the total losses minus armature Cu loss. So now it is equal to total losses is 3042 minus 564.5. It is equal to approximately 2478 watt, 77.5. So it's 78 watt light. This is the WC. Now, in second case power output power output is equal to how much it is given. See here, when the power output is 7.46 kilowatt, when the power output is 7.46 kilowatt. So let we consider that let IA is the armature current at 7.46 kilowatt power output. So we can say that IA, then I is equal to IA plus ISH, which is equal to IA plus 4 ampere. So this is nothing but the current drawn by motor. This is nothing but the current drawn by motor at above load condition. Whatever the here it is 7.46 kilowatt. So therefore power input is equal to power output plus armature Cu loss plus constant loss. So it is equal to power input. Here, this is the total current drawn by motor. So it is V into IA plus 4 ampere. It is power output is 7.46 into 10 raised to 3 is the output. Whereas armature current IA square RA plus WC is the constant loss. So it is 200 into bracket IA plus 4 is equal to 7460 watt plus current IA and the armature resistance. So we write in this way plus 0.06 IA sphere plus the constant loss. It is 2478 watt. So by solving this equation, we get a quadratic equation as 0.06 IA square minus 200 IA plus 9138 is equal to 0. So by solving this quadratic equation, IA is equal to 200 plus or minus under root 200 square minus 4 into 0.06 into 9138 divided by 2 into 0.06. So we get armature current. There are definitely two values. So one value will not be a correct. So the correct value will be near to the previous current. So it is a 46 ampere. So here 46 ampere is the current because the other value is maybe a 3000 or more than 3000. So now, therefore, current drawn by motor I, or it is I, is equal to IA plus ISH. So it is 46 plus 2, sorry, 56 plus 4, it is equal to 50 ampere. Already in the numerical it is given. So once we know the concept, we come to know that the answer may be correct because when the output is 20.2 kilowatt, the current will be 101 ampere. Now in the second case, the output is now only 7.46 kilowatt. It means that it is smaller than the first case. So definitely when the output is smaller, the current drawn by the motor will be definitely smaller than the current drawn in the first case. So first case is a 101 ampere. So the armature current in the second case or the total current drawn by motor will be a 50 ampere. So power input is equal to V into I. This is the new value. So 200 multiplied by 50. So output is 10 kilowatt. We know, sorry, input is 10 kilowatt, whereas output is as no as output is given, output power is given 7.46 kilowatt. Therefore, the efficiency is equal to 7.46 divided by 10 into 100 equals to 74.6%. So this is the efficiency of motor at this particular condition. So Let okay. The next example is a 200 volt 14.92 kilowatt DC shunt motor when tested by Swinburne's method gave following results. Running light test. It is the no load test. Armature current is armature current was 6.5 ampere. So here it is given that I0 no load current, light condition. So 6.5 ampere, and the field current ISH, it is remains same. Either the motor is loaded or not loaded, 2.2 ampere. The armature logged means under the stationary condition of the armature or rotor, the current was 70 ampere when the potential difference is applied to 3 volt. It means that suppose this is the armature circuit. Armature. Here the voltage is applied across the brushes only by disconnecting the armature. It is applied. How much volt? It is the 3 volt is applied. And because of application of this 3 volt, the current flowing through the circuit is 70 ampere. Definitely it is going to flow from the armature resistance. It is the RA. So what is the value of armature resistance? RA is equal to voltage divided by current, 70 ampere. So under such condition, the armature resistance is 0.0428 ohms. So this is the resistance. Instead of giving directly, estimate the efficiency of motor when working under full load condition. So the motor is running at the full load condition. Okay. So we have to find the results at full load condition. So it is given that armature current. So therefore the current armature current is given IA0 is given 6.5. So I0 is equal to IA0 plus ISH, which is equal to 6.5 plus 2.2. It is 8.7 ampere. So this is the no load current. Therefore, no load power input equals to the voltage is 200 volt multiplied by 8.7 equals to 1740 watt. This is the power input at no load condition. Now the constant losses. Constant loss, which is equal to no load input minus no load armature CU loss. So no load input is nothing but 1740 watt minus no load copper loss. It is IA0 sphere RA. So it is equal to 1740 minus 6.5 into bracket square into 0.0428 ohm is the resistance of the armature circuit. So it is equal to 1738 watt approximately. This is the no load input, sorry, no load constant losses, WC. Once the constant losses is known, again let IA is the armature current at full load. The nameplate reading is the output rating. It means that in the numerical, it is given that the motor is 14.92 kilowatt. So it is not the input power, it is the output rating. The nameplate reading, whatever the data is given, it is the output power, output conditions. Therefore, we can say that armature, therefore, current drawn by motor is equal to IA plus ISH. Whatever the value of ISH is given, that current plus this one is the total current. So here, if you draw the DC shunt motor, so this is the shunt field current ISH, and this is the current IA, and this current is I. The voltage is V. Okay. So we can say that power input is equal to power output plus armature CU loss plus constant loss. So the power input is nothing but V into IA plus ISH. This is the total current, V into I. Instead of writing IA plus ISH, power output P out plus armature copper loss. So it is a IA square RA plus WC is the constant loss. So here it is 200 volt. The power input, the voltage, rated voltage is given as 200 volt into bracket IA plus shunt field current, it is 2.2 is the shunt field current, equals to power output. The power output is 14,000. It is a, how much it is? It is rated of the motor 14.92. So it is 14,920 is the power output. Current armature resistance is point, armature resistance is point, it is 0.428 IA square plus WC is the constant loss 1738 watt. So it is equal to, by this calculating this one, it become a quadratic equation whose the equation is like that 0.0 428 Ia square minus 200 Ia plus 16,218 is equal to 0. So by solving this equation, we come to know the value of armature current Ia by solving above quadratic equation. We get armature current Ia is equal to 84.7 ampere. So once we know this one, therefore current drawn by motor I is equal to Ia plus ISH. So current I is equal to 84 plus 2.2. It is 80. So it is 82, 84. Okay. This is the 82. Armature current is 82, not 84. It is 82.5 ampere. So it is 84.7 ampere. So once we know the power input V into I, and it is equal to multiplied by 84.7, so 16,940 watt. So definitely this power input is greater than the power output. So therefore efficiency is equal to output is 14,920 watt divided by 16,940 watt. So efficiency of motor is 88%. So by this way, uh, as no load data is sufficient to calculate the efficiency and copper losses, that is the variable loss at any desired percentage of load condition. So this is the say advantage of Swinburne test, that only one data is sufficient. Therefore, higher capacity motor can be tested since the load is under no, the method of testing is only under no load condition. So this is the advantage, that higher capacity motor can be tested. But what is the drawback? The drawback is that since we are not loading the motor or we are not loading the machine at its full load condition, so it is not possible to examine the temperature rise of motor, vibration, sound, bearing condition, and commutation, bad commutation, that is the sparking over the brushes. So these parameters cannot be accounted by this method. So this is the drawback and limitation of the Swinburne test. So thank you for listening. Next time we will meet with the next method, that is the Hopkinson test, or it is the regenerative or back-to-back test. Thank you.